Like,
I feel like that's what I do every month.
and I don't know, I just did like everyone.
Okay. Well, big class,
Yeah.
Big numbers.
big numbers, wide numbers. That's good because we're also in like a very mood. So,
You are?
yeah,
Oh,
but we're gonna do our best today. So sometimes you show up even when you're not in it.
yeah.
Yeah, so that's what we're gonna do today. We're gonna try and finish up a discussion about two of the more important probability distribution functions. And then we're gonna talk about how we use them in physics. So far we've been talking about math and gambling. None of which is physics. But we do wanna sort of tie this back to what you may end up doing professionally, which would be how. Yeah, well, it might be gambling with other people's money, but it might also be in the context of trying to understand, like, look for meaning inside of data. And so that's when we'll get into the idea of what statistics are as opposed to probability. Okay, so what was the Poisson distribution?
You want like the words you gave or the equation you gave?
I would like words first, and then I'll like the equation. What did it mean to you?
I don't remember, and the only words I write down are the values of x that can be chosen, and the range could be infinite, but it has to be discrete.
Okay, good. So that's almost all of it, right? So let's just put those words together and find out what they mean. So let's go back one step more to the binomial distribution. So what are the requirements of the binomial distribution and what kind of distribution is it?
Discrete and two outcomes.
Good. So discrete, choosable sides and two outcomes. So what are the discrete options here? Yeah, those are the potential. Can I use the binomial theorem for all of the different choices here?
Yeah, evens or odds.
Okay, evens or odds, you have to choose one or the other, right? Is it even, right? Or the opposite of that. So I can't use every single coin, every single side. Right, so you could say, is it 6 or not? Is it 2 or not? Okay. So then the natural place that we were going after that was to say, okay, well, so what's the larger distribution we could think about? If we want to talk about the grocery store problem, which you all then went home and you thought about in great detail, right? You didn't just immediately ignore that part of class. You said to yourself, how many people can be standing in front of me when I go to the grocery store?
At most, every person on earth.
At most, every person on earth, good, right? Because you could have a really bad day, and at the least, 0. So no negative people and no half people. So that would still be discrete, and the range could be very large, right? So practically speaking, we could imagine that stores like Costco or a store like Rite Aid might have a different rate at which people stand in front of you in line. And those rates we called lambda. Okay. And lambda was defined essentially as the number. So this is, why is it coming off that? This is the number of trials. And P is the individual probability. Such that NP is finite in the limit that n goes to infinity and p goes to 0. Something going to 0 times something going to infinity is a constant. Okay, yeah, weird, right? But that's okay. And so this is essentially something like what is the expected number of people, or maybe the peak number of people, depending on how we want to discuss this probability, that might be standing in front of you. And your expectation might be that Costco had a larger one. Right? So more people tend to stand in front of you at Costco than at Rite Aid. Okay, good. So in practice, what does this look like? The probability distribution function, f of x, looks like
Oh, alright. Bottom has x factorial.
Oh, times e to the power of negative lambda. Times lambda to the power of x.
cool. A lot of really good numbers, right? Okay. And what did I give you as homework? Not real homework, but do it over the weekend.
It was to estimate the probability that like a certain amount of people would have to be in front of you. And like given store.
Did you do it?
I went to Costco.
I went to Costco. I did the experiment. Okay. So let's try.
Yeah, let's try.
Okay, so let's imagine, I wanna know, because I need to get out there really quickly. What's Costco's?
It's like,
Say like 25.
Costco's 25, okay, Lambda's 25. Okay, and I need to get out of there really quickly, so I just want my chicken bake and I'm fucking leaving, right? And I'm really curious about x equals 5.
You're gonna go 5 times.
No, this is the probability that there's 5 people in front of me.
Oh.
Exactly 5 people in front of me. Okay. This is the number of trials.
Yeah, I don't know why I saw it.
Oh, okay, okay, good. So let's try this out. Is this calculable?
oh,
The equation just has lambda and x.
okay, so for P, is that so P individual probabilities, is that like approaching zero or like will always?
Do you need either of these?
No, I do not, because lambda is empty, and if we were just.
Right, when we think about the binomial distribution, you can look at a coin or a dice, and you can see the choices. And therefore, the probability of each of those choices is finite. Right? If the number of choices becomes infinite, the number of outcomes could be infinite, then each of the probabilities can do one of two things. It can either go to 0, or it can go to some asymptotically small value.
Okay.
Right? Because the multiplication of them needs to be finite in certain cases.
Okay.
Especially for the Poisson distribution. The reasonable?
I'm pretty sure in math now, you can just, get factorial, but you press F, and then just like alphabet this word.
I read what you had.
Oh, I don't know.
You put your pen down. It was very authoritative.
Yeah, you.
When it's taking a different part of the thing, you most likely get
I usually use my computer and I forgot how to use this.
Okay.
You're gonna find it too?
It's on here.
Do you know where factorial is on here? I did the math button. I think it might have been 20 years since I've used this.
Well, 5 factorial is.
20. 20,
5 times 4.
120?
20.
really
How
small.
big?
10⁻⁶ power. 1.1 to the negative 6.
So should you be expecting to have 5 people there?
No,
Get there?
no,
Which direction do you think it's more likely to have people?
probably like more so towards 25.
We said 25 is
Yeah.
likely.
Exactly. And so there's the fun thing about the probability distribution. That you can draw it fairly easily. So let me draw a couple different versions here. 0, 1, 2, 3. So for 0, 1, it looks like this. It just kind of keeps going down. That. Whereas if you were doing something with like, this would be lambda equals 1. It's gonna shift. As lambda gets larger, lambda equals 5. Then you're gonna have very few points out here, 1, 0. Kind of bigger. 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 And then you can peak right at like here. You'll notice a few other things too. Which one of those distributions, and I know, I'm sorry, they're in the same color, yeah. Yeah, lambda is the product of all of the potential outcomes and the probability of each of those outcomes. Assuming that they have something like equal probability. So here, as the probabilities go to 0, number of potential trials goes to infinity, then lambda is something like the you'll see in 2 seconds what it means. Okay. It means what you think it means. So let me ask you a different question, right? You see this probability, and let's say I drew it really well. Okay, here's 1 and here's 5. Anything you notice about the probability distribution width?
It looks sinusoidal.
What's that?
It looks sinusoidal. Like
Um,
if you
go
merge them together,
only have between 0 and 1 probabilities. Okay, interesting. So you use the word Gaussian, which I've never heard of before. We haven't learned that in this class. But interestingly enough, what I was trying to point out here is if I drew a curve over it, which you shouldn't because it's discrete. Okay. Here's 1. Good. Which is wider?
The land equals 5.
N equals 5. It's clearly wider. But is there a rest of the other one?
No, there is.
There can't be a rest of the other one, right? Because you can't choose negative numbers. 0 to infinity in this case, right? Okay. So let me ask you a different question. Okay? This is a real life question, one that we deal with all the time. I'm gonna get an email, some number of emails today. Unfortunately. Let's assume that the emails arrive random. What is the probability that any particular hour 0, 1, 2, 3, 4, or 5 emails are received? If the mean number of emails is 2. Normally I get 2 per hour. What is the probability of x 0, 0, 5? Again,
Right.
I don't know. Grab a number that's shown.
You know,
Could you repeat the question?
there are a lot of reading things.
What?
Are you read them all?
Just, yeah, what is the first one? X equals 0.
0.13 or 1 4.
Okay, is that what everyone else got?
Yeah. And then for x equals 1, 0.27.
Same thing for the next one. 1 8. Here then. Yeah, 1 8.
No, I'm gonna do x equals 5, but then, sorry, for x equals 5, it's 0.36.
Point.
Oh, 0.036.
That probably jumped up a lot.
Yeah, it took me.
Okay. So what does this mean? You're sitting in the office, you get 2 emails an hour. And all of a sudden you get 5 emails an hour. How do you interpret that?
And then all of a sudden you get 5.
Is it normal?
Like,
It's not a likely outcome. Will you expect then to get another 5 in the next hour? Probably not. Right, unless the mean is wrong, right? Unless this number goes up randomly. Right, but then this isn't a very good distribution. So if you say, well, I just got 5, so I'm unlikely to get any for the next hour, right? That would be a way of interpreting. Because this, for example, is an unlikely event, right? And you're much more likely to be in this region, somewhere between 0 and 3. So now we have to ask 2 questions, and you kind of have been hinting about them. So what is lambda? Or another way of asking that is, what is the expectation of the x of the Poisson distribution? What's the thing called again?
That should be the expectation, right?
Yeah, what's this called in like normal words?
Oh, the average.
Good, or the mean, right? Good. So you don't know this, but this is lambda. Okay. And the Poisson distributions are really cool. But what about this one? What's the variance of x? What does that mean again?
how much each individual value of X varies from the average. Or like,
Remember, this is talking about the variance of the distribution, right? We're talking about shapes here.
oh,
What does this one tell you?
that, yeah, it does, yeah, mu does tell you about variance, because I remember it's like X minus mu squared, that should give you variance.
Okay, so let's take a break for a second. Let's think about the shape. What does this tell you about the shape?
Where the most stuff is concentrated,
Yeah, it's sort of like where it's peaked,
Yeah, with peak of the graph.
and this tells you the
how
Width.
spread out the peak is.
width. Good, right? So sometimes we write it like this. Okay, sigma squared. And this for Poisson distribution is also lambda. That's correct. That's the correct phase. Huh? What the fuck? So the width of the distribution is also controlled by lambda. But you noticed that earlier. You saw that when I drew it up here, right? Okay, so the wider the distribution goes, the more that it's gonna go off to the right. Make sense? Okay, so now we're gonna talk about the thing that I didn't know what you meant earlier, but now I have read the book, and so now I'm for the first time learning this word, Gaussian. What is that? Or normal distribution? Okay. So my favorite thing about physicists, they call things normal. Wait, what? What do you mean normal as opposed to what? Abnormal distributions, right? Okay, so what's the Gaussian distribution? What does it require? Is it a discrete distribution? Is it continuous?
It's continuous.
It's continuous because it can take any value. What else?
It always has a shape.
Yeah, so very characteristic shape, right?
So
And what do people tend to call it?
Gaussian curve
Yeah, there's another word for it.
Like,
of the average.
Smooth bump. Okay, so some people call it a bell curve.
Mhm.
So it looks a little bit like a bell, say, or, like this.
Yeah.
Okay. Okay, so let's write the distribution down. Continuous. This form. So it has some fun features here. See any fun features?
Yeah, you get the variance, so X minus mu, but then it's over 60.
So even before we think about the variance, just look at the functional form for a second. What does the functional form tell you about it?
And EXP means the E to the.
E to the power, yeah.
So it's E is something squared.
E to something squared, so it must be symmetric, right? Good, that's great. We can see that it's centered around mu. Thank you. And you can't see it right now, but it has width. See? That's the idea of where that signal comes from. So those are all on purpose. This thing here, you don't know where this comes from? Circle. Close? What's that? For any probability distribution function. Correct. Good. So it comes from the normalization requirement. So if you simply start with this functional form, 1 over lambda, sorry, 1 over sigma, and this stuff here, and you take that integral from minus infinity to infinity, you get 2 pi. Sorry, square root 2 pi.
So if you go from where to where, you get to square root of five.
If you take this, and you leave off this thing here, and you take the integral from minus infinity to infinity, the area under the curve is the square root of 2 pi. So you must divide by the square root of 2 pi at the very end in order to make sure you get 1.
Okay.
Make sense? So if you look at this shape, here's your Gaussian. Whatever, okay, and you don't divide by this. Let's imagine that that is the shape that you use for this. Then the space underneath this curve. Great, okay. Make more sense?
I mean, the area of every Gaussian, oh, it will always be 1.
We won because we normalized it, but if we hadn't, then it would be that case, right? Okay. Good. Okay, there are some fun things that we can write here. What is the expectation value of this? Of the distribution? This one's the obvious one. That would be the normalization here. So what's the expectation value? Remember what expectation value means again? The average. So what would I write the average as?
Would it be new again?
Yeah, good, very good. All right. Sometimes the stupid answer is the right answer, right? Okay, and what's the variance here? What's that? Sigma squared, very good. It's important that it's sigma squared here, and you'll notice here sigma is a square root of that.
Both of those equal lambda.
Well, no, lambda was only present here. We have not talked about how we construct the Gaussian distribution yet. And I've given you the functional form. Okay. So maybe that's a perfect lead-in. So how do you construct the Gaussian distribution? When you are going from what is essentially the binomial distribution to the Poisson distribution, binomial is when you flip a coin or you can roll a single die and you have a finite probability and a finite number of trials. Here you can have the same number of infinite trials, but we are going to keep the probability not going to 0. Okay. So in fact, there is a little bit of a, one can become the other can become the other. So for example, the Gaussian distribution can become the binomial distribution, right? And similarly, the Poisson distribution can become the binomial distribution. Another way of saying that is the binomial distribution, when you use very, very large numbers, becomes Poisson. And similarly, the binomial distribution, if you use large continuous numbers, would be the Gaussian. Does that make sense? Okay. Because this is symmetric and the width is sigma, some fraction of the probability will be enclosed at different parts here. So you've heard things like a 1 sigma result. What does that mean?
A good result.
But
I can't hear you, John, you gotta shout.
A good result.
A good result. It's very close to the average.
yeah,
Okay, we're gonna come back to this probably when we talk about data analysis, but a one sigma result is actually not better. So,
well,
so 60% of your outcomes will fall pretty close to the mean, right? And it's not whether or not it's a good or a bad outcome, it's a measurement of how far from the mean is it. Whether or not it's good or bad has nothing to do with it. Does that make sense? Okay. So in particular, if I say something like a 3 sigma outcome, what does that mean?
Your data is very varied.
What's that?
Your data has a lot of variance from, so you get a lot of like,
But I'm using a Gaussian distribution. The variance is right there.
that's not very likely.
oh,
Aha, so now I said that the result is 3 sigma. So that means that the result is 3 sigma away from the mean. And if I look at this width, here's 1 sigma, here's 2 sigma, here's 3 sigma. So the outcome here represents a small fraction of the likely outcomes. So this is an unlikely result, not whether it's good or bad. You see? So we're agnostic about the quality. We're only describing the likelihood that you got that answer. If I got a 5 sigma result, is that, first of all, is that possible? Is base
Yes.
closer to 0?
not-
No, and we have plenty of
Ah,
high sigma results. So yeah, 5 sigma is basically 0 in that it's very unlikely. But depending on how many times you run the experiment, you may or may not get a 5 sigma result, right? Because this is indicating the likelihood of it happening. And we've all seen this type of crap, right? We've bet our entire fortunes on probabilities that are smaller or higher than this one. You hear what I said?
Oh, no.
I said sometimes we bet on probabilities, which may be as low as this, and we lose our entire fortunes, right? So we were all familiar that if you run those experiments over and over, you should win out. But if you get a 5 sigma result, that's neither good nor bad. Does that make sense? Okay. Sorry, I didn't mean to like stab you. Nice. Okay, just thought it was relevant. Prime example. Okay, so there may be one more thing that we'll talk about here, just really briefly, and just to keep our brains awake. I'm gonna make you do more work. I hate it, Chris Money. So in particular, I'm very curious, I have a student who's working for me and I want them to find out the outcomes that are within some range of our experiment, okay? And so I have some probability distribution function that the data is centered around, and I think that it's Gaussian. And I'm really curious how much fall between 1 sigma minus and 1 sigma plus. This is minus 1 sigma, and this is plus 1 sigma. Does that question make sense?
Yeah.
Okay. So we could write the cumulative distribution function. That's this, it's a different symbol. This is the probability of z being less than some other smaller z, right? Which would be something like 1 over the square root of 2 pi times the integral from minus infinity to z, that location, wherever you want to go to. Okay, and it's just going to be the exponential. I'm going to use a standardized version here where I'm going to assume that mu is 1 and sigma is 1. And so I'm just going to do like this. Make our math easier. Does that make sense? How you would do that? You can do this with any Gaussian. So instead of thinking about things in terms of their true values, you can, of course, take your data set. And you see that this section here, I said was centered on the mean. So when I have that difference, x minus mu, you could replace that with a different variable, x minus mu, being the transposed x to the mean. And similarly, after I divide by the width, you can think of this entire value here as a new variable, x minus mu or sigma, just being called u. Make sense? You draw this. Make sense? Why you would do that?
You go over there.
Yeah, so inside of here, we're thinking about different Gaussian distributions. But they're all gonna look the same, they're all gonna look like a bell curve. And the only thing that's changing is how wide they are and where they're centered. So if I want to think about properties of them, I may as well use a reduced variable where I set this equal to 1, then I don't have to divide by it. And I set this equal to 0. Right? And that would tell me all of the properties of a Gaussian distribution. And then the only things that would happen afterwards is that it would either become wider or more narrow, depending on how I change sigma. And it would either move left or right, depending on how I change beta.
Yeah.
Okay. So I can use this new variable u to describe it. Okay.
I forgot if that was a 2 or a Z on the bottom. That's a.
That's just the two. That's this one here. Oh. All right, so let me ask you the first question. What is the probability of this is location 1 sigma away? So this is -1.
Oh, based on the graph above.
Based on, yeah, based on this, I mean, this is the formula, right? So here's the integral from -infinity to z. Give us a little more space here if we want.
We need to know U and sigma, or if we solve it in terms of the. We'll get a U and then.
Well, we won't get a u, right? We're integrating these right to u. So if we think about this in the context of, right, what I said to do here was to think about this as being centered at the origin. So that mu equals 0 and sigma equals 1, right?
At the end of the integral, does it say dA or dx?
du.
Ah, thank you.
Was that a negative, U squared? Okay. Oh, I got an answer.
Okay.
0.158.
Yes, I'm seeing
Is anything less, or anything greater than, is the, and,
it. Oh, so I'm getting Z is -1.
Yeah.
I,
What did their folks get? Same thing? Okay, now let's ask the second question. What about out to this point? The 1?
okay.
0.841? Believe that?
Yeah. I got the same thing agreed.
Interesting, all right, so 2 versus 2 or 2 versus 1, who's on whose side?
So the C is less, so that'd be everything to the left, which is positive 6.
Yeah, we're integrating from this direction.
right, yeah.
So this one no one was upset about. Now we get out to here, and this says something like 84% of all of the distribution has already been counted.
That makes sense.
Do you believe that?
Yeah.
Now you believe it?
Yeah, I like that.
Wait, say it one more time.
Okay, so we're counting from the left,
Mhm.
going that way to the right. When we got to here before, no one had a problem with 15% of the distribution living out on the left-hand side.
I was from left to right.
Yes, from left to right. So we're integrating from minus infinity to z. Right? And that's the integral. Minus infinity to z. There to there. Okay, good. So we head into 1. Okay, you said, okay, 15% of the total distribution exists from minus infinity to -1. And then you go all the way up to 1. And now Reed claims, and Rolando agrees with him, that it's 84% of the distribution. Is that correct?
We actually did this.
Like,
Oh, yeah, one.
Yeah. I mean, how many sig figs do you have here?
no, yeah, this look, the last little like, if we go from 1, and then if we go greater than 1 on the other side, then you just add those. and it should be the other
If
side.
it's,
That's right.
no, because the probability it's less than 1 is like
Yeah.
more of a distribution than -1.
Yes, that's true. So let's have a look here. I mean, even if you take the argument that they're having right now, if you add these two numbers, how far are you off? Well, you're off by, if I just add these two together, I get 0.999.
It makes sense to have.
It's pretty good, right? So if I use a couple more sig figs, I might be right.
Yeah, it is actually 9.
But why would you add them? Because the less than 1 overlaps with less than -1.
Ah, good question. Why would I add them?
It's the same as for the polymer version of polymer.
Because it's symmetric, I can use this piece here and say, well, that's the same as this piece here.
Oh,
And right, and we're just checking our work just to see what we're doing. And let's do some other fun sort of sneaky stuff. Okay, now I only want to know the probability of x, probability of -1 z 1. So I only want to know this region now.
Okay.
Oh, that? Yeah. I meant these things.
Yeah,
What I want?
I got it.
Okay, what do you got?
I got 0.683.
0.683. So 68% of a Gaussian is found within 1 sigma of either side of the mean. Okay, You will hear this value quoted for the rest of your physics life. 68% is the probability that your value will be found 1 sigma from the mean in either direction. Okay. Okay. I'm not gonna have you calculate it here. So this is the 1 sigma result. What's the 2 sigma result? Point 1 going 2 sigma away, out to here.
Oh.
I don't think you can guess it, you have to calculate it like we did before. Because you have to go up to 2, and then you have to go out to 2, and then take the difference, right? Or you'd have to go between -2 and 2 here.
You're gonna go for 0 with it? Oh, no, because you're going.
I just want it in between.
Okay.
Yeah.
So this is another one that you'll just know by heart. 95%. Three sigma result.
Probably bigger.
Bigger, very good. That's correct. It didn't get smaller. It'll be 99%. Great.
So that means if you were to have, like, with, like, if you were to have data with like 1 sigma. Of like. All the data within 1 sigma is like greater or less than 68%, then it's not considered a Gaussian curve or a Gaussian process.
So say that again. So if you have a bunch of data
Yeah,
and you see most of it is outside of 1 sigma.
Yeah.
Yes,
okay,
that would be unusual,
that would be,
right?
Yeah.
So one of 2 things could be going on. Your sigma was calculated incorrectly, right? It's probably the more standard version. Or it's not Gaussian. But most data is Gaussian,
okay,
or some form of that, right?
okay.
So it's very unlikely that you'll be dealing with. Okay, I think there's only one more point I want to hit here before we start talking about, I was gonna show you the derivation of the Gaussian approximation of the Poisson distribution, but I'm guessing you guys don't care. Is that correct? You wanna see just the derivation really quick?
So the derivation of what?
The derivation of the Poisson distribution from Gaussian. Okay, we're gonna move on. That's not anywhere as important as the central limit theorem.
Okay,
Just for, completeness, of course. There's one more distribution type, which is the uniform. Uniform distribution, silly, but it's fine. Here's what it is. The piecewise function, 0 everywhere outside. And between A and B, it is 1 divided by B times A. Okay. And you're welcome to calculate the mean and variance if you want. What's the mean? It's A plus B over 2. That would be the average of the endpoints. What's the variance? Less obvious, but it's E minus A quantity squared over 12. Okay. You're mostly gonna see Poisson distributions. Sometimes you'll see something called a log normal distribution. Sometimes you'll see something like an exponential distribution. They're just distributions. They're just functional forms to how numbers are distributed. And the things that we really care about are these quantities, the means, the widths, and probably as you get into more advanced topics, thinking about higher order moments and what that tells you about the shape of the distribution. how are these numbers distributed, right? I'll say one more thing before we move into statistics, which is the central limit theorem. I know this is probably driving you crazy that I'm moving backwards across the board, but you know what? That's just the type of week I've had. So we're gonna do it. Here's the central limit theorem. Very powerful. You heard this before?
Central limit theorem? I actually don't think I have.
It's also called the CLT, not to be confused with its tastier cousin. Thank you. I knew someone was on my side. Okay.
I was really cute. What is that? You got a cute
Okay. DTLA, no. Okay, so the central limit theorem is just a statement about how pervasive Gaussians are in all of probability theory. And essentially what it says is if you have xi where where xi such that I equals 1, 2, all the way out to n, which are independent random variables. Examples of this might be the distribution of heights, the distribution of weights, the distribution of intelligence, or money, or genders, right? Each of which could be defined by a probability distribution function, f of x, right? Where f of I, x, each one has its own distribution function. With a mean, mu I, and a variance, sigma I squared. Okay? Then you could construct a new variable, okay? Such that z is the mean of them, sigma I xi over n. Okay. Which would mean that the expectation value of this new variable that you construct about these, you know, multiple random variables will just be sum of the means over n, however many you have. Its variance will be the squared sum of the widths and as n goes to infinity, z becomes there's some probably beautiful proofs that if you really want to see, we can do off the charts. But the idea here is that if you take large enough distributions, large enough samples, everything starts looking Gaussian. That's why they're so fucking ubiquitous in science, right? Okay, so there's lots of really fun stuff. If you check out both in BOAS and in the rest of this book, in the probability section, stuff about joint distribution functions, having multiple variables, how you generate moments for each of these. You know, I kind of just threw this up on the board and told you to believe me. But you didn't actually see me do this expectation value of x, right? So that's all found in your text if you're interested. But unfortunately, as much as I want this to be a 15-week class just on probability, I'm not allowed to do that. I have to teach you other things. Okay, so now we're going to talk about the section that I promised you, which is real life, not gambling. Okay, yes, you're excited? Okay, so in fact, In practice, you may or may not know what the distribution of your function is. So you may take data and have no idea whether it is Gaussian distributed. Because Gaussian distributed data has certain requirements. One of the requirements for a Gaussian distribution is that the data is uncorrelated. That is to say, sampling one thing won't affect a sample nearby. And that's not always the case, right? Especially when you're thinking about particles or you're thinking about entrapped states, something like that, okay? So in particular, you might be thinking to yourself, maybe the simplest example is, what if I don't know what distribution I have? How can I be confident, let's say I sample, grab some pieces of data, do the experiment 6 times, 10 times. When am I done? How do I know that I have got all the properties of that distribution? And how confident am I in those answers, right? So we've sort of shown you the distributions at first and said they have these things called means and modes and blah, blah, blah. Okay, so now I'm going to show you data. And you're going to calculate things and you're going to see this is where ambiguity lies. But this is also where the physics is as opposed to the math, right? Physics happens at the data, math is the interpretive tool. Does that make sense? You want this still? All right, it's all disappearing forever.
Oh, okay. I can tell you those.
Hold on, this is- Okay. So we are essentially going to be talking about the word statistics, what that means. Statistics are things that we create about the data. Okay. I want you to imagine for most of what we're going to do here that we're thinking about real world experimentation. And we're trying to understand underlying information that is not known. Does that make sense? Okay. So you can imagine that the product of an experiment might be, say, n results. And the first time that we do this, we're going to think about it in the context of, say, single numbers, but that is not necessarily the case. So for example, I'm going to run an experiment. And here you have a die. You have information that the experimenter might not have, because you can see how many faces it has, right? You ran the experiment with your eye. But suppose you didn't have that information. Suppose I only gave you the outcomes of the rolls, right? So I roll it one. Roll it again. Roll it again. 6. I roll it again. 4. What do you know about the die?
There's at least 4 options.
There's at least 4 options. Good. Anything else? No. Nothing else. Because we don't know how the sides are distributed, right? Nothing came up twice. So they're equally likely, but maybe not. Because we only did it 4 times. Right? That's not nearly enough to determine probabilities. Those would be the underlying probabilities, not what we saw. Because if you do an experiment a couple of times, you can get very wonky answers. Okay. Alright. I'm not gonna let that one go. Just gotta remember that, okay. So let's try a couple things here. Any set of measurements, let's say we have n measurements, that construct something like xi. Or sorry, let's do this, x1, x2, x3 out to xn, right, n experiments. Any function of these is called a sample statistic. Sometimes they call them just statistics, but you really want to think of them as statistics of the sample themselves. Okay, so I'm going to give you numbers, ready? 188.7. 204.7. 193.2. 169.0. 168.1. 189.8. 166.3. And 200 even. Okay. What are things we could construct about this data set? The mean, that would be the most obvious answer, right? How do I construct the mean here?
Because they all, like at the moment, it looks like each one has like the same weight attached to them. Do we
Do
just,
you know anything about weights?
no, I just made that assumption because none of them repeated. There's no-
Sure, but even if they did repeat, would that make one of them more likely than the others?
That's true.
So when we think about the sample, we have to construct measurements such that they tell us something. And then we are going to assign meaning to those arbitrary decisions. Because I'm about to show you something that's very stupid. And so you said, read something about the word mean, right? You said this. And how did you want to do the means?
Add them all up and then divide by.
You wanted to add them all up and divide by the number. Is that correct? That is what type of mean? Normal. This is an arithmetic. Magic. Okay, is that the only mean there is? No, there's other means. Good, what's the next mean?
Is that the one with weights? Where it's like the summation of x, f of x?
We don't know anything about f of x, remember?
That's,
You have to cast from your brain, cast aside all hidden information. All you have are these numbers here. Are there any ways that we can construct a different mean using only the numbers themselves? Come on, folks, you gotta be creative here. Let's make up new magic.
Draw me a line from the middle,
What do you mean, draw a line from the middle?
like the number like 1, 2, 3.
You can do that and then like, identify, make up a signal, right?
Okay, so this is using add.
Yeah. Oh,
Let's multiply.
Use mean multiply.
I'm gonna take every data point and I'm gonna multiply them by each other. Okay. And then I'm gonna take 1 over n. Okay? This is called the geometric.
What's that symbol?
You never seen that?
It looks like pi.
It is pi, it's a big pi. So just like we do a big sum
What
like
does it
this,
mean?
means multiply all of the individual elements. Okay. And you said, wow, that was really fun. I loved inventing new math. They're just funny. So let's do the next one.
There's another mean.
there's 4.
We're
Alright.
Wait, good night.
Okay, so here we have n on the top. Okay, and then I'm going to do the sum on the bottom. I'm gonna go 1 over xi. Okay, this would be the harmonic mean. What does that look like to you? Well, that just looks like the opposite or the upside down version of the arithmetic mean.
So they're basically multiplying each other.
What's that? Well, because remember that this sum is 1 over x. So it's 1 over x plus 1 over x plus, and so it's a little trickier. Right? Okay. And then my favorite one. It's just the most outrageous. Here's the sum. We're gonna add them, but we're gonna square them first. And we're gonna take this for root away. And this would be called the root mean squared. Okay, so there's 4 of you. Please calculate the averages.
Okay,
Select one, shout out first, which one do you want?
on the geometric.
Harmonic.
What do you want, what do you-
I'll take it.
Okay, and let me know what they are for these numbers.
For the geometric, you got 184.426.
You got for the,
got 185. 5.2.
which one did you get?
Root mean squared.
What do you have?
183.87.9.
What was your first digit?
0.9. I just read.
184.975.
Okay. So which is right?
None of
Take
them.
average of those.
All of them.
Take the average of those, but which average do you take of the averages?
Just keep going.
It's averages all the way down. So this is the first time that I really want you to think about this process that you've ingrained in your brain so easily and never thought about. And that is Reed's immediate answer. You simply add them all and divide by n. Who taught us this? Right? There's nothing wrong with this, right? But this is what we've believed for so long. And yet there's perfectly fine ways to construct information about any sample. This is our sample, right? And this tells us stuff about the sample. Right? Just like we had for our distribution, we had the mode and we had the median. That tells us different stuff about the sample. Is one of these better than the others?
I don't see why not.
You don't know yet, right? They're useful in different circumstances. Now, of course, the most common one is the arithmetic one, right? So that's fine. We'll see that it has limitations as well. This might be more useful in certain contexts. That makes sense? Okay, so let me ask you a different answer. So what is the mode and the median of this data?
Okay. Well, I know what they mean, but what is the actual, what are the proper way?
What is the mode of a sample?
The value that shows up the most. right?
Good,
None of them.
there isn't one.
Yeah, there's-
There are no repeated numbers. Okay. Or you could choose any.
Not any data to construct.
Or you could choose any.
No.
They're all just as likely as none. Zero is definitely incorrect. Zero is a number. Right? The mode is any number is the mode, because any number there is just as likely as any other. Okay, what's the median?
You like to do it in grade school?
Because that when you draw on the line and you put it in the middle.
Exactly. Exactly. So let's look here, okay? Where's the outside edges? Here's the furthermost to the right. And here's the furthest to the left.
I can just
Yeah, 30. So is it just 160, 169, 5/2? Is that how
I'm
we're
doing
doing
it
it?
basically. So. 185.5.
Not quite.
Wait, so with median, there's an even number?
You divided by 2, huh?
Do you get like the middle two in that five?
I think so.
I just think the edges and subtract them divided by 2 and then add it to the bottom.
So that would be an average of all of them.
I didn't do all of those. The edges, I found what was in between them.
But you don't have a value.
Sorry, so I'm saying that's an average of those two numbers, right? That is not necessarily the definition of the median. The median says a range.
I think the distance. between
Okay.
Yeah, but
So the definition for the median is to arrange the numbers in ascending order or descending order, however you want, and find the center.
Yeah.
If there's two numbers, you take the average of the two numbers in the center.
Okay.
168.
There's two numbers.
Not 160, it's in the 80.
Wait, can you repeat what you said again?
Yeah.
Uh,
So if you have a bunch of numbers like we have here.
Yeah.
First, you arrange them in ascending or descending order. So this one would go to the top and then this one next. And after you go down the list, you find the middle of the list. So there's 1, 2, 3, 4, 5, 6, 7, 8. So that would be whatever takes up these two positions.
I thought it
Positions.
would be the middle or ruler, like where there's spread out and then find where.
Well, the median tells you about the numbers you have, not about the range that they exist in. So you might have, for example, one row, 166 in here, and everything else is sort of more centered around 200. The median is gonna be not as sensitive to outliers. So it's gonna look for where most of the numbers actually come from.
About 189.
There we go. Good. So now which metric is best? Root mean, okay, so which metric is worst? The mode tells us basically no new information. The median tells us something, right? The median tells us where this distribution is centered more or less. But so do all of these other measurements of the mean. And they're all telling us something slightly different, right? Okay. So we're gonna stop here, but when we start up again on Wednesday, we'll talk about how we construct things like sample means. And more importantly, sample variances. And what we'll be looking for there is knowing that we have some sample that we're drawing from. We are going to ask, is this sample after X number of experiments, how close is it to being correct? Okay, and that's where the real fun is.
I think correct as in like. Words that you're gonna cross.
No, as in representing the true mean. Right, so let's say I sample something a bunch of times. How many times do I have to sample it before the value that I'm getting is representative of the real number? Because if I just sampled this die once. Right, I just roll it once. Well, let's do it like this. There's two dice. Uneven distribution. Okay, and I read the info. And I get 7. Oh, shit. That's the sample mean on the first try. Okay, well, let's say I didn't get a 7, let's say I got a 2, right? If I just sampled it once, you know, my mean of the numbers that I got would be 2, and that would be incorrect. So how many samples do you have to take? How many sample means do you have to construct in order to get a representative sample that's reasonable?